So the first problem that I would like to discuss with rotation is uh, basically a curved road. Oops. All right. So if we are on a road which is curving, say something like so, and even if the road itself isn't circular, like for a piece of it, it's basically circular. And if we pretend that the curve is part of a circle, then we call the radius that would go with that circle the radius of curvature. So if you're getting on the highway, an on-ramp will have a typical radius of curvature somewhere around 50 meters. If that's so, and the posted speed limit for an on-ramp is, say, 45 miles per hour, which is a pretty typical speed, the question is, what is the minimum coefficient of friction you need between your tires and the road in order to make the turn? Assuming you're traveling at the maximum posted speed and not above it, which I'm sure none of you ever do. All right. We'll call the clockwise rotation here the positive direction, and that actually takes care of our first two steps. This is basically a one-dimensional problem. Well, I mean, it's not a one-dimensional problem because the centripetal force that we're going to be looking for is toward the center. So maybe we'll draw that in. Right? There has to be some friction helping you make this left-hand turn. Okay.
Wait, wouldn't that F stand for force, not friction?
So
Because,
usually I use capital F for force and scripty F for friction.
okay.
Um,
Oh, so the friction is going towards the center, not towards like the back of the car.
so the rolling friction that you have when you're just driving is pretty minimal. It's there for sure. Um, but for this purpose, I'm going to ignore it because we're not super concerned about your straightforward movement. We're mostly concerned with how we're going to get the centripetal force we need to not run off the road. So it's definitely worth considering in some cases, but not as super important here.
So weight is not gonna be considered either.
Well, that is a good question. I actually want to draw a second picture to help us see what's going on. So we've got a bird's eye view already. I'd like to draw a view that's maybe taken from the car behind you. So if someone is coming behind you, then they might draw this force diagram, right? You've got your weight, You've got normal force. You've got friction. And from this perspective, we might say actually that to the right is the positive x direction and up is the positive y direction. So far, so good?
Wait, no. So what's the friction that we're considering here? Because to me it looks like centripetal force.
Well, centripetal force is not a force that's acting on your car. It's a force that your car is required to provide in order to stay on the circular path. Right? So something else has to provide the centripetal force. And in this case, the thing that's providing the centripetal force is the friction of your tires on the road.
Oh, so that F is pointing down into the road as opposed to towards the center of the circle?
Not down into the road. So remember, friction is parallel to a points parallel to a surface. So if you like, anyone ever driven on an icy road? Right? If you're trying to make a left turn on an icy road and you haven't got any friction with your tires on the road, then you try to make a left turn, what you end up doing is you slide to the right. That is, there's no friction available to change the direction of your speed, so you just skate. That's not a fun place to be in as a driver. So if you do have friction on like a dry road, then the friction is what lets you change your direction.
Okay. So, okay, thank you.
All right, so let's apply Newton's second law here. Well, I mean, I guess we shouldn't skip a step. Before we apply Newton's second law, we want to break up those forces into vectors. So maybe we say normal force is only in the y direction. Weight is also only in the y direction. And friction is only in the x direction. Jasmine, it doesn't look like the friction is parallel to the road. Yeah, that's more a statement about me as an artist than anything else.
So are we not basing our vectors on the drawing with like the radians, like the circle one?
We could. So if we were going to write down what our force here looked like, here our weight would have to be coming out of the page. Right, so, and yeah, Pamela's got it. The in pink and green over here is a bird's eye view. So we're looking at it from straight down. So, right, so if we wanted to look at it straight down, we could do, we would end up doing a sum of forces, say in the z direction, that's up and down. A sum of forces in the theta direction, that's around the circle. And then lastly, a sum of forces in the radial direction. And we could definitely do that. In fact, maybe we will do that in a minute, just to see how the two perspectives compare. But in our kind of boring gray version here, if we want to apply Newton's second law here, then a sum of forces in the x direction and a sum of forces in the y direction is appropriate. All right, so sum of forces in the y direction is the easy part. Our car is not sinking into the road or flying off the road, so we would very much like the net force in the y direction to be 0. So N and mg must cancel each other out, so the normal force must be equal to the weight in this case. In the x direction, now remember, our friction is going off to the left because we're constantly making a left turn on this on-ramp. So if we're moving on this circular path, the sum of forces in the x direction is not 0. Right? Sum of forces in the x direction has got to be our required centripetal force. Because if the sum of forces is not mv squared over r, then we are not traveling on a circle. Also, since it's to the left, we need a negative sign there. So we expect the sum of forces in the y direction to be 0 just because there's no movement in the y direction. Right? Our car isn't moving up or down, like in the vertical direction, and we would very much like our car not to move in the vertical direction relative to the road. So unless we're having a particularly bad day, the sum of that forces in the y direction has got to be 0. All right. That's enough gray-blue for one page. All right, so the sum of forces in the x direction is the new piece that we've added with this chapter. So we want to connect these two pictures, this pink and green and this gray-blue picture. But the friction is pointed in the same direction. We've just rotated our viewpoint, right? So the friction is going to the left of the car, which is pointing toward the center of the circle that we're traveling on. And if we're traveling on a circle, even briefly, so like a piece of an on-ramp is basically circular. So if we're traveling on this circular path, then the net force pointed toward the center of the circle has to be mv squared over r. Because if it's not mv squared over r, we don't have the required force to stay on the path, and so we don't move in a circular motion. Which, in this case, if we're going on an on-ramp, not moving on the proper circular path is going to mean we're having a really bad day. And we need to call our car insurance. It's negative just because I said to the right was positive up here.
Is this Fx that we are finding, is that the centripetal force?
Yes.
Okay.
So
And then
in fact, if right, this x direction in the blue picture is the same as the radial direction in the pink picture.
And then the reason why it's just negative m or mu n over here is because there are no other forces acting in the x direction, right?
Right. We've only got one force that can possibly do the work for us. So if we had, so in a bit, I'll share another problem, and there is definitely a possibility that we would have other forces helping us to provide the necessary centripetal force, but in this case, we don't. Okay. So let's chew on this for a minute. So if we have mv squared over r on one side, mu n on the other, I'm going to go ahead and cancel the negative signs. And from our consideration of the y direction, we know how much normal force we must have here. And actually that lets us cancel out the m's as well, which means actually that the size of your car, like the weight of your car, doesn't have any bearing on the safe use of an on-ramp. So if we want to figure out what the coefficient of friction between tires and road has to be, we can just divide off g. So mu equals v squared over rg. We actually have enough information to just get a number on this thing. So we have our velocity, but it's given to us in miles per hour, which, let's be honest, is kind of a yucky unit. Let's convert that to meters per second. So there's approximately 2 miles per hour for 1 meter per second. But to be honest, I use Google to do my unit conversions on a frequent basis. So if you just Google 45 miles per hour to meters per second, it'll come up and say, oh yeah, it's 20.12 meters per second. Letitia, you said weight doesn't play a factor in centripetal force. That's why they canceled. Yes and no. So weight doesn't play a factor in centripetal force here because it's just in the wrong direction. Our weight is perpendicular to the direction that centripetal force needs to be in, so it can't contribute to the centripetal force. The cancellation, I think, is more of a happy accident. It's like a little Bob Ross happy accident. Okay. So if the velocity is about 20 meters per second, I'm totally going to round that 20.2 to just 20. So 20 squared is 400. Our radius is 50, and g is 10. So that's 500 on the bottom. All right. Coefficient of friction of your tires has to be at least 0.8 to to safely make that turn. Good news, if you've got relatively new tires, your coefficient of friction between your tires and a dry road is probably more like 0.94. So you've got friction to spare. The unit on, so the coefficient of friction is unitless, because we have, velocity squared on top and bottom here, basically. All right, so that's our on-ramp problem. The 400 came from converting our speed to meters per second, and then 20 squared is 400. All right. Let's talk about spiders. So a spider can grip with a force equal to 20 times its own weight. It's one of the many reasons that spiders are kind of awesome. But let's consider a not awesome place to have a spider. Let's say that there is a spider on your ceiling fan. Your bed is also an acceptable answer for where is a bad place to have a spider. I used to have this this black cat. She's passed now, but she was never very clean. One time she came up on my bed for pets, and I was petting her, and a spider crawled out of her fur. I didn't quite scream, but I did not react well. So we have a spider on a ceiling fan. Spider is half a meter from the center of the ceiling fan. The ceiling, you go to turn on the ceiling fan, and because the spider can grip really well, it doesn't fall off right away. However, your ceiling fan accelerates at a rate of, say, 0.25 radians per second squared. So, how long can that spider hold on? I think the proper units for this, or the proper coordinates rather for this problem, we want to consider maybe toward the center of the circle and counterclockwise, because that's the way your fan spins. So we're going to have some centripetal acceleration and some tangential acceleration. And so we'll just go ahead and define that as the positive radial direction and the positive angular direction. And that is step 1 and 2 taken care of. All right. So the spider will be able to hold on until the magnitude of the total force it's experiencing exceeds 20 mg. So the total force experienced by the spider, what variable do I want to call that? You know what, maybe I'll just call it capital T. So the force experienced by the spider is going to be some nope, I'm already using capital T, so I can't use capital T again. I'm going to call it Q. We're not using Q for anything else. Right, so we're going to have some tangential force in the theta direction and centripetal force in the radial direction. So the magnitude of the total force, right, we're going to use the Pythagorean theorem to add that up. And the max this can be is 20 mg. All right. And now we're on to the physics part. We want to use what we know about centripetal acceleration and angular coordinates to try and write this, magnitude of q as a function of time, so that we can solve for how much time it would take before the spider flies off of the ceiling fan and right into your lap on the couch where you're watching TV. Letitia, that's right. If Q gets to be bigger than 20 mg, the spider goes flying. And everybody has a bad time at that point. So let's work on this first term under the radical, this left term under the radical first. We know that there is a relationship between the angular acceleration and the tangential acceleration. Right? We established that a few slides ago. So we can actually replace AT with alpha times r. Alpha and r are both things we know, so that's awesome. That fixes our first term under the radical. Our second term under the radical is going to take a little more work. We know that the centripetal acceleration that we need to provide in order to stay on this circular path, we know that it's got to be v squared over r. So Now, just like we know that there's a relationship between the angular alpha and the linear a, there's also a relationship between the angular speed and the linear speed. So we can write that the linear velocity is equal to angular velocity times r. And if we plug that in up here, we get m omega squared times r. All right. Which doesn't seem like a huge improvement because we don't know omega yet either. But we do know that our kinematic equations apply. So if we pull out K2, we can say omega equals omega naught plus alpha t. Omega naught is 0 in this case. So we just have alpha t. So this piece we can rewrite as m alpha squared t squared r. Okay, and that actually gives us a function of time, which is exactly what we wanted. So using that information, we can rewrite our piece under the radical as m alpha r squared plus m alpha squared t squared squared r all to the 1/2 power, right? 1/2 power is the same as square rooting. Oh, whoops. Yeah, I ran out of room to write that effectively. So I'm going to try that again. Give us ourselves some room to finish this off. All right. So the first thing I'm going to do is expand those squares inside the square root. So we get m squared alpha squared r squared plus m squared alpha to the 4th, t to the 4th, r squared, all of that square rooted. There are some common points in both the terms under the radical. Like there's an m squared in both of them and an r squared in both of them. So I'm going to factor an m squared r squared outside the square root, right? And when we take it outside the square root, m squared r squared becomes just mr. And we've got a mass on both sides of the equation, so that's going to cancel out. Right, so far so good. I'm going to divide the r off to the left-hand side of the equation. So we're going to divide the r off. And then we're going to square the entire equation to get rid of the square root on the right-hand side. And then the algebra from here is pretty simple. We're going to subtract an alpha squared from both sides and then divide by alpha to the fourth. And also I'm going to expand this square that's on the left over here. So we have 400 g squared over r squared minus alpha squared all over alpha to the fourth. And on the other side of the equation is going to be a t to the fourth. So actually I'm just going to take this whole thing and fourth root it. There we go. Questions or comments?
Yeah. When we took out M and R, couldn't we have also taken out an alpha too?
Sure. We could have taken out an alpha, and that would have left us with 1 plus alpha squared t to the fourth still inside. That's perfectly okay.
Can we resume to the previous step when we broke it down and found out the MAT and MAC? I just want to know which are the things that we're expected to know in terms of formulas.
Yeah, let's go back for a second. So the knowledge that we made use of here, we made use of like our definition of, that color is way too light to be making check marks. So we made use of our definition of angular coordinates. And then we made use of our definition for centripetal acceleration. We returned again to our definition for angular variables. And then lastly, we used the kinematic equation.
Thank you.
Yep. Did that answer your question?
Yeah, it did. I was just confused where we got it from, but it makes sense now. Thank you.
Jasmine, yeah, omega 0 is 0. The fan wasn't on until you walked into the room, flipped it on, and sat down on the couch. Which is why you're about to have a spider surprise. I'm not actually going to do the plugging in numbers part of this because, I mean, it's, for the one thing, it's anticlimactic at this point. And for the second, I still have one more problem I need to present in the last 15 minutes of class here. Since you took an m, wouldn't there be an m inside the parentheses? Well, I factored out an m. So like this m and this m got factored out of the two terms under the radical. And then when you take the square, like when I brought them all the way out of the square root, actually. So square root of m squared is just m, where it then canceled with the m on the left-hand side of the equation. Oops. All right. Last problem of the day. Thank you all for sticking with me. We're going back to the on-ramp. But this time we're going to make a little bit of engineering decision. So any of you who've ever gone on an on-ramp probably have noticed that the on-ramp is not flat, right? Most on-ramps are actually tilted to the left or right a little bit. And we're going to examine why that is here. So remember when I said everything, like many things were basically a box on a ramp? Well, here's a car on a banked curve. And the banking of the curve is not much, right? It's usually tilted like 5 degrees. Right, there's your car, again viewed from behind. And if we draw in our forces, same forces. We're just tilting them a little bit now. And I know earlier when we did a box on a ramp problem, I tilted the coordinate system to make it simpler. I'm actually not going to do that in this case. So I'm going to say that to the right, actually, you know what? To the left is positive x, and up is positive y. So when we go to break down the vectors, we're going to have to do a little bit of work, right? Here now, using this definition of coordinates, our weight will be only in the y direction. But we're going to have to work a little bit for our normal force and our friction. Right? And again, we have to decide, well, which one of these two other angles is theta? So I'm going to draw the same sort of diagram that we did last time. All right, so this angle's theta, which means so is this angle, and this angle. Right? So every second angle will be theta because we're walking around, identifying all the 90-degree angles. So if we take a look, we want the angle, so if we take a look at this angle here, that's the angle between the vertical and the up and to the left, right? That's the same as this angle right here. So theta is on the top, which means that we have n sine theta in the x direction and n cosine theta in the y direction. We're going to do a similar thing with the friction. And here, right, this angle right here, well, that's actually the same as this one here. So there's our theta. So our x component here is going to be f cosine theta, and our y component will be f sine theta. You have questions or comments on the breaking down of the vectors? Okay. Now we can apply Newton's second law. We're going to start with the y direction. So sum of forces in the y direction we expect to be 0. Right? We do not expect to be flying up into the air or sinking down into the ramp. So we would very much like there to be no net force in the y direction. So that means we have minus mg plus n cosine theta minus f sine theta. Of course, f is just mu times n. So we can factor out an n from both of these terms, and we can get like something like n times cosine theta minus mu sine theta equals mg. So the amount of normal force must be mg over cosine theta minus mu sine theta. Little bit different than our flat on-ramp case. All right, let's do the same thing in the x direction. So the sum of forces in the x direction, what are the sum of forces in the x direction going to be? Letitia's got it in 1. It's going to be centripetal force, because we're still making that left-hand turn. Right, so it's got to sum up to mv squared over r. And the forces we have in the x direction are n sine theta and we have f cosine theta there, but I'm going to replace the f with mu n, just like we did in the last step. So mu n cosine theta. All right, I'm going to replace both of these n's with what we got from the y direction. And actually, I'm going to factor that out front. M cancels off again. And I'm going to ask a slightly different question, actually. So we had, if you'll remember, in the first time we looked at this problem, we discovered that if the top speed is 20 meters per second, then we need a coefficient of friction of at least 0.8. So I'm going to ask the opposite question here and say, if we've got a mu of 0.8, what's the maximum safe speed? Well, there's a lot of junk on the right-hand side here, but we actually know the values for everything on the right-hand side now. All right. So we have G is 10. Cosine of 5 degrees is like really close to 1, right? Because cosine of 0 is 1. So cosine of a small number should be close to 1. In fact, cosine of 5 is 0.996. And then mu is 0.8. Sine of 5 degrees is similarly going to be a pretty small number because sine of 0 is 0. So sine of 5 is going to be like 0.087. And then we have the sine theta and cosine theta appearing again. So we have 0.087 plus 0.8 times 0.996. And on the other side, still v squared over r, where r is 50. Anyone have a number for me here?
I have a quick question. If we're doing everything in radians, shouldn't we convert all the theta to radians as well?
You could if you like. In this case, since we're only using the trig function of an angle, it doesn't matter. But if we wanted to put an angle into our kinematic equations, then it absolutely has to be in radians. If we're just taking the trig function of it, then we just have to be careful that our calculator is in degrees or radians mode as appropriate.
Thank you.
Mm-hmm. All right, Jasmine says she gets 6.6. Yeah, 9.28. That's what I got, approximately. So then v squared is going to be 50 times 9.283. Take the square root of that. There we go. So, by tilting the road by just 5 degrees, we increased the maximum safe speed by like 8%. So if you're interested in, if you're a municipality and you're interested in, reducing traffic accidents on on-ramps, one obvious solution is to tilt it so that the normal force from the on-ramp can provide some of the centripetal force, and then don't change the posted speed, right? Post the max speed still at 45 miles per hour, but tilt it a bit to give all of your drivers a little bit of safety margin. So Jasmine, if you're calculating everything on the right-hand side here, that's not v, that's v squared over r. All right, let's work through this a little more slowly then. So in the numerator, we have a 10. That sine theta plus mu cosine theta, so 0.087 plus 0.8 times 0.996. That's a factor of 0.884. In the denominator, we have 0.996 minus 0.8 times 0.087. So that gives us a factor of 0.926. So 10 times 0.884 divided by 0.926 is, well, it's not 9.28, but it's actually 9.54. Right, so 0.884 is smaller than 0.926, but not by a bunch. So 0.884 divided by 0.926 is a little less than 1, but not like a ton less than 1. So 10 times something a little less than 1 should be a little less than 10. The 0.884 is this factor here, which comes from the sine theta plus mu cosine theta. Yeah, Parentheses is the number one source of trouble on calculators. 100%.